Good evening to all of you. Thank you everyone for joining with us in this wonderful evening. So we have got here Prof. Haravindan here. So let me give an introduction. Good evening to Prof. Haravindan, IESL committee members and fellow engineers. First of all, on behalf of IESL New South Wales chapter, we acknowledge the traditional custodians of the land which we gather and meet today. We pay our respects to their elders, past and present, and extend our respect to all Aboriginal and Torres Strait Islander peoples here today. First of all, let me thank Prof. Thiru Aravindan for accepting our chapter's request and delivering this valuable lecture for members. It is the time now and privilege to introduce Prof. Thiru Aravindan to our audience. Prof. Aravindan is currently a professor of structural engineering within the School of Engineering and Centre for Future Material at the University of Southern Queensland at Toowoomba. He is a graduate from University of Peradeniya, Sri Lanka, and holder of Master of Engineering and Doctor of Engineering from Saitama University, Japan. After obtaining his PhD, he has worked as a senior research engineer at DPS Bridgeworks, Tokyo for 3 years. During his stay, he involved in the R&D for an award-winning innovative bridge design with large eccentric external post-tension cable bridge successfully constructed in Japan. Prof. Haravindan is a chartered professional engineer and a fellow of Institute of Engineers Australia and a registered professional engineer at Oregon State, USA as well. His expertise and research includes fiber composite structures, pre-stressed concrete technology, structural rehabilitation, and in engineering education. He has used fiber reinforcement polymers, normally called as FRP, to create innovative structures for civil and infrastructure applications. He is actively involved in national and international organizations, including Engineers Australia, Composite Australia, and International Institute for FRP in Construction. He is a council member in the International Institute for FRP in Construction. He has over 30 years engineering experience in the industry, research and academia involved in several industry-funded projects. He has been recognized with several prestigious awards for excellence in research, in addition to learning and teaching. He was part of the team that was awarded the prestigious JEC, the Japan Economic Corporation Europe 2014 Innovation Award in the oil and gas category for the development of a novel composite clamp for pipeline repair. The novel clamp developed by Prof. Haravindan's teams, the world's first composite solution designed for in-situ repair system for pipelines with through-wall defects. The innovative solution was developed with the industry partner Petronas, the leading oil refinery company from Malaysia. But not last, I am proud to mention Haravindan has mastered Japanese language during his stay in Japan, and he is very fluent Japanese speaker now. We welcome Prof. Haravindan now to deliver his valuable presentation. Thank you.
Thank you, Janaswati, and good evening or good afternoon, wherever we are in. I believe we have got participants from Australia, in New South Wales, or in Brisbane, and some other places, and also from Sri Lanka. So it is nice to give this presentation. So as I will probably start sharing my slides. Hopefully you can see that one. Okay, thanks. So what I would like to present today is about the innovative composite structures for sustainable civil infrastructure. And just going to the presentation, it will probably have about 35 to 40 minutes, followed by question and answers. That's the way we will have this. And I would like to first again, I would like to acknowledge the country. We are working from University of Southern Queensland. We acknowledge the traditional custodians of the land and waterways where we are located, and further we acknowledge the cultural diversity of Aboriginal and Torres Islander people and respect the elders past, present, and future. And I know there are people in Australia who are meeting today, so wherever you are dialing in, so we acknowledge the traditional custodians of the land you are in today. And similarly in Sri Lanka also, we do have our native traditional people in Sri Lanka. I think we need to acknowledge their presence and their traditions as well. Thank you. So first, giving a short background about my career history. I graduated from University of Pennsylvania and worked as a junior staff member for about 3 years, and then moved to Japan to do my postgraduate studies. So after completing my master's and PhD, I worked as a senior research engineer in a prestigious company in Japan, and from there moved to Australia in 2002. So now it has been around 20 years being in Australia at University of Southern Queensland. Started as a lecturer and currently a professor in structural engineering. So I have also taken a role of Associate Dean for Research and Research Training for about 6 years, and also last year was Head of School for Engineering and Surveying within our university. And so probably you may be wondering where USQ or USQ, University of Southern Queensland, is located. It is located, the main campus is in Toowoomba. It is close to Brisbane. And also we have got Springfield and Ipswich campus. So that's where university is located. It is close to Brisbane. And then the overview of my presentation. So today I'll talk about just about our Center for Future Materials, where I have been conducting the research, and also highlight the facts about where we are using composites in the civil infrastructure, and some of the past case studies, recent research and development, and talk on some of the challenges and future opportunities with concluding remarks. So if I talk about composites in Center for Future Material, we do have a Center for Future Material. I'll share that one. So the Center for Future Material, we in short call it as CFM. It's a research center at our university, and that was established back in 1995. So now it is close to 35 plus, close to 25 plus years, and that it has changed name for Center for Future Material. Last for a couple of years, it is called as Center for Future Materials. So as you may see from the slides, what we have got is we have got several industry partners, and we attract industry funded projects, and we work with industry partners and also through government and other organizational funding. And over the years, we have developed a niche area in our composite research, and it has been known for that. And we have in fact, 4 research priority programs. One is on advanced composite manufacturing. Those who are in the manufacturing industry, you will be knowing about how composites are used. And also we use functional materials. Civil composites is my area, and one of my former PhD student, now he's a professor as well. He's leading that one, Professor Alan Manalo. And then also we have work on geopolymer and concrete areas. So these are the 4 themes we have got in our center. And if I go and show some of the facilities, so you can see we have, this is one of the unique university and a research center that has got facilities in the form of where we have got a characterization of materials. We can do thermal analytical results, TGA, DGA, anything with composites. And also we have got a very heavy strong flow that can go up to 2 meganewton kilonewton 2 meganewton or 2000 kilonewton capacity of strong flow structures for heavy testing. And then we have also got testing facilities for fire testing and so on. Then on the processing side, we have got a pultrusion with full winding and braiding technology, and VARTM and high temperature furnaces and environmental chambers and so on. And also in simulation side, we use abacus ANSYS and various other materials. And on non-destructive testing and methodology, we also have optical microscope and SEM and so on. So these are some of the facilities we have got, and that should probably indicate the usefulness what we have in our center. And we have got external partners, including universities and research organization and industry partners, both locally, nationally in Australia, and also internationally. So some of the industry partners, for example, Wagner's, they are a local-based company, but they manufacture things and export to overseas as well. So that is something I'll be also touching in on my presentation. So I'll go back to my presentation here. So I had talked about the CFM, the Center for Future Materials. So now I'll go back to what has been the main factor of composites. So when we talk on FRP, fiber reinforced polymers. So most of us think FRP is just you put some fibers in concrete and mix it and use it. I think that has been the traditional style of using FRP in civil engineering. But in Australia, when we look at, we can use it in new forms, in innovative forms. One of the things you will find in Australia, as I mentioned earlier, it's a very large country, a continent itself, and there are a lot of timber structures. Timber railway bridges, timber poles, timber piles, railway sleepers, all made out of timber. And in fact, if you look at the material of timber, it is the natural fibers that brings the timber material, the timber, the tree coming out of that, it is natural fibers. So can we use composites? That has been the main factor there. And when I started back in 2002, the first thing I was able to see is this truck in a quarry truck that is about 75 tons of a truckload. And that bridge, it's not a pre-stress or a concrete bridge, it is a composite bridge. So that was done as a case study, and I was able to witness that when I first came to Australia. And from there onwards, what went up is the next one to an actual road bridge in 2003. That was in Roma Creek Bridge in New South Wales. And that's where the first composite bridge was done as a highway bridge in Australia. Then there were several other developments were done here. As I mentioned, Wagner's is the industry person who is the company that has developed. So several road bridges has been done in New South Wales in Australia. And then this particular one, it's a new generation of composite bridge. This was initially started as a trial in 2007. And this is part of our university bridge as well in a walkway, and we have done full load testing on that as well. So when I talk about composites here, I'm talking about pultruded sections, sandwich panels, various other materials, and the FRP, the fiber, mostly in civil infrastructure, glass fibers are used, and automobile and other industry, aerospace, carbon fibers are used, and there are hybrid fibers as well. And in some cases, they use Kevlar or aramid. So there are different fibers being used, but the prices of carbon is very expensive. So automobile and space industry, yes, when the lightweight and price is not a problem or not a major issue, they use that. But in civil infrastructure, where there is a lot of materials to be used, the price become a key factor in selecting what is a suitable material. So here we are using glass fibers, and here what you can see, these are not steel hollow tubes, but it is a protruded section made out of glass fibers and vinyl ester resins here. Different resins are being used, vinyl ester, polyester, epoxy, but here these sections are being used with vinyl ester resins. And what you will see here, not only these straight longitudinal fibers, there are cross fibers, which is going in plus minus 45 degrees approximately. So here what we have is the manufacturing method is known as pull winding technology. It is pulling as well as winding technology that is being used. So when we have these different cross sections, very similar to steel cross sections, square cross sections, hollow sections, so then we can make use of that, and that's what we have done in the form of research and development and making to actual commercialization through industry partners. So you can see these are all these protruded FRP protruded sections has been used here, that is as a column and cross girders, and then the whole thing is a bridge walkway here in addition to the side of the road where that has been used. So another pedestrian bridge, this is back in 2007 that has been done. Again, protruded section with a top of sandwich panel on top of that. That makes the reality of protruded sections are being used. So here again, you can see in a lot of national parks and other areas where you can't take heavy machinery, the lightweight of FRP materials make it advantage. With very lightweight equipment, we can manufacture and transport that into place and make that also, feasible with the natural environment. For example, you can paint this one in green color, in a natural this one, or in a brownish color like that. So this is across a river way, and this has been done by Wagner's CFT, Wagner's Composite Fiber Technologies. So here is a good example about where a typical timber bridge that has been rehabilitated. I'm keen to know there are a lot of engineers here. Maybe some of them are civil engineering graduates or undergraduate students, and there are maybe even others who are working on the materials. So all of us, what we study back in our university is we study a lot about steel, we study a lot about concrete, we study a lot about pre-stress, but not many of us study about timber. But traditionally, timber structures has been used for so many 100 years. And fiber composite is the artificial, or it is the artificial fiber compared to a natural fiber of timber. So here we have got a bridge here. And if we take about that bridge rehabilitation, that bridge can be rehabilitated with this. Here you can see the previous timber girders has been replaced with fiber composite girders here, and you have the cross girders as well and the main girders there, and then on top of that you will put the roadway, and the whole thing is being a replacement case study. That's what has happened here. And another important aspect is we can also use sandwich panels. So sandwich panels, so earlier we had a company called Carbon Lock. What they specialized was in developing sandwich panels. So here again, you have a mat type of one, trimax in the 3 directions, the main direction and plus minus 45, and that can go through a curing process in that methodology, in that manufacturing process, and out you get like a similar to a panel, what we might call as a plywood panel, but this is a composite panel that is coming, and this is cut to around 2.4 meters, a typical height of a house height in Australia. And this can be used in wet areas and in also various construction process, and that's the way that sandwich panels has been done. Now, how do we use these sandwich panels in a bridge cross section? So what you see here in the top left picture here, so this has been done with those sandwich panels in the form of webs. And here on the left bottom, what you see is that decking system is made out of sandwich panels. So that's what you are seeing here. So we have the main girders with protruder sections coming there and a cross section done. The beams are done. And on top of that, the sandwich panels has been placed. And that makes a 10-meter long bridge. And what we have done here, this was done back in 2007 period. So we had done the full scale testing, load testing has been done. And in fact, we measured the temperature on this bridge for over 1 year at different locations. The top of the bridge, the bottom of the bridge, in between the ambient temperature and so on. Why do we have to do that? Because people, I'm sure there are some materials engineers here who know the TGA, the glass transition temperature of some of the resins used are much lower than what a steel can withstand. So some of the epoxy-based resins and vinyl ester resins, so due to the TGA, which is only around 80 degrees or some cases, high temperature are allowed up to about 100 degrees. So if the natural temperature is reaching around 60 degrees due to a bushfire or some fire that goes on in Australia, that happens a lot, a bushfire in a lot of regional areas, the temperature in some of these places, so you had to protect those structures. So in fact, on a summer day, we had 40 degrees temperature, the ambient temperature, but the temperature on some of those decking system and near the girders, we measured close to 60 degrees of temperature. So you can see how much temperature variation we might have in a structure, and then what materials and what properties we need to use as a design engineer or a materials engineer who is specifying what's a suitable materials to be used in different environment. So that's the things we learned here. And of course, that bridge decking, the decking system has been used for pedestrian bridges like that. And again, various in national parks and other areas with very lightweight lifting equipment, you can install the bridge very quickly. So that's one of the advantage. So here you can see a good example about how an existing timber bridge. So basically this is the existing log, either 17-inch, those days in inches, 17 or 19-inch, which is 375 millimeters or 425 millimeters thickness or log or diameter. That has been replaced here with a bridge with girder with sandwich panels and protruded section. So that has been replaced here. So the two girders, what has been replaced here, there are two different types. Two different companies came up with to replace a timber girder. Wagner's company came up with like an I section using protruded section and top and bottom laminated panels, where the other company came up with carbon lock. They came up with sandwich panels and a combination of hybrid protruded sections. So this has been used to replace those. And what you can see, it is not, when we do experiments in the laboratories, testing one or two beams is good, easy, but manufacturing hundreds of these, you need to have a good manufacturing technology and also able to proof load and testing. So as part of the project which I was involved in 2010 to 2015 period, we tested over 60 of these beams from Wagner's CFT and 30 out of these beams. And these 60 beams were manufactured in 3 different stages, improving the developing the methods. And this was done in 2 sets. Out of that, 90 of those beams were tested, and some of them have now gone to actual road bridges. So here, if we look at the bridge testing, you can see from the sandwich panel and protruded sections, what we see here, this is the cross section. The sandwich panels comes as the webs here, and hybrid protruded sections are used here. And then the test what we have done, bending test as we shown here, and the shear test. While bending and shear will give you the strength of it, But the fatigue test on a road bridge is an important test. So we had to do a 2 million cycle fatigue test in selected girders on this. And also drilling and other crushing tests had to be done, because then only you can make sure these things can work on site. So fatigue test, why? We will have roads, the vehicles that goes on roads. So if you are talking about 60 years of lifetime or 100 years lifetime, then based on the traffic loading, about 2 million cycles or 5 million cycles had to be done. So that's the kind of the testing we have done. From there on, we go on to see how it can behave. But as engineers, as structural engineers or civil engineers or materials engineers, we study about characterization of the various materials and the behavior and based on the material, the behavior of the structure. For example, you will have in steel, you will have what is known as ductile linear behavior. After ductility, it goes flat for a certain period. But in timber or in fibers, if it is pure fibers and things, fiber is the main dominant one, what you will get is a failure like a linear behavior and a final sudden failure. If we get this, how do we design this? We had to have relevant safety factors and have relevant design loads appropriately when this kind of behavior is done. That is what is done in a lot of timber design, timber structural design. And with the other material, what we had used, we had two different type of girders. In this girder, you can have a linear behavior straight and then a little bit of ductile behavior. Pseudo-ductile behavior is also being shown. That is due to the hybrid materials they have used. So between these, we can use and select appropriately and design them in a road bridge or a girder for the road bridge. So here what you can see here from simple experiments, mass manufacturing, and this one has been put in an actual road bridge in Australia. So that is where I would call how the research and development goes into reality. So while we do experimental work in a university, whether you're an undergraduate or a postgraduate or a PhD or after PhD do research, yes, you will work with people and then that will go into reality as well. That's where it starts as a small research and major development, manufacturing process, and then it goes into reality. That's an important aspect here to note. In addition to these bridge girders, we also, I have told about, yes, we had a lot of timber sleepers. Like in Sri Lanka also, I'm sure there have been a lot of timber sleepers being used. Those have been replaced with pre-stress timber sleepers, pre-stress sleepers, pre-stress post-tension or pre-tension timber, pre-tension sleepers being used, manufactured. That is a new trend. But there are areas where you had to replace some of these existing timber sleepers. How do we do that? So we call it the transom is a rail sleeper that is on a rail bridge. So what we have done again, so here the sandwich panels has been trialed as a small experimental case. From there, that's a full sleeper to go on a railway bridge. And here, this is an old railway girder that has been there, but on top of that, those composite transoms or composite sleepers has been placed, and that in fact had been placed in Newcastle, close to Hunter Valley area in Australia. This was done back in 2007-8 period. So what you can see here is there are this old timber. This one has been still maintained or not maintained. It has been kept there, but they have put the new composite sleepers. But you can see the older sleeper is a little bit lower than that. That is for the risk or the fail-safe mechanism, because when you put these things for the first time on an actual rail bridge, where in Australia, the rail that takes some of these cargo trains that will take them coal mine to the port, that is one of the heaviest loaded railway lines in Australia. So in that case, they want to make sure in case something happens, until they test and prove it, they left the old sleepers below, but it is not really touching the rails there. So that's how it was tested, and after that it has been manufactured and simplified. And so this is one of the coal carrying rail is going to the port, and that has been tested as well. And then from there we have done further testing on improving for a typical standard railway line using composites, and how that has been manufactured and put there. This was done through one of our postdoc fellows, and that is now in place as well. Again, rectangular composite sleepers has been done. So you will find why a traditional sleeper, a typical rail line can be used with that kind of shape. That is all fine. But there are areas when two lines meet, you will need a same kind of cross section and a longer section. That's why these rectangular composite sleepers have been used. So from there, typical full railway line, you can go with the typical shape, and we have done testing here in the laboratories, and those are actual trials in the field. So that is being practiced as well. Some other aspects, we can also think about rehabilitation of piles. There are a lot of timber broadwalk and piles there. So here again, what you will see is, particularly in the tidal zone area where the water comes and goes up and down due to tidal, this one, you will see a lot of deterioration over time. So this was done in Shorncliffe. So what they had to do is, they said they want to maintain the lower side of it, but remove part of it and use a composite pile system. So what we have done here is to connect it to the existing timber below. So that shape was done, and then connect it to a new pile, composite pile on top with a composite connector there. So when we did this, we had to do manufacturing of this was done by the industry partner. Then we did full scale testing in our laboratories, and then that was changed. So you can see here, that's a composite pile that is sitting here. Some of these are existing piles. Some of them are covered with concrete around that timber, but this one is a new composite pile. That's the way some of the pile installation and rehabilitation has happened. So not only pile driving can be also done. So here the full scale testing is being done in our laboratory, and then you can see using pile driving equipment, these are driven. So this 10-meter long pile has been driven up to 6 meters. This is already gone on the ground over 6 meters. So this is a composite pile, not a steel pile, not a timber pile, but a composite pile that has been done and driven. So here again, a lot of in marshy area, in water area, steel piles does not last long, but a composite pile which can resist corrosion can be used, as some of the broadwalks has been done. So here again, pile driving and how do we do that with existing equipment is an important trial that need to be done as well. So in fact, one of my former PhD student back in those days had done pile driving test, repeated impact test. So they had to simulate this one. How will the pile driving will impact? So what you will see here, the top part of that where the pile is being driven, you will get damage. Then you have to make sure you can cut that off and how far the damage can go. And that type of testing and research has been done so that in practical side, we can design and make sure things are working. So here again, it's a composite pile rehabilitation. So the pile and these even cross girders are made out of composite structures, and that is an existing bridge has been rehabilitated with composite pile systems. This is an interesting case study where this is the Brisbane river walk. That's a Brisbane river. Some of you all might have heard. Again, we had a fairly heavy weather condition in the last 2 weeks. New South Wales is also some parts are affected. Brisbane river area that was affected as well. But back in this area, so this is the river, Brisbane river area, and this timber walkway, we had issues there that has to be rehabilitated again with composite pultruded sections being used. and sandwich panel was used on top of that. So it is a combination of the sandwich panel and composite sections here, and that is a rehabilitation after that. And by the way, this particular one, it did undergo the flooding system that happened in January 2011, almost around 11 years ago. So it withstood that flood, and now we are having a similar flood last week, and now things are coming back to normal life in Australia. So let me share some of the recent development also that is going on here. So I will share that one. So here what we have is we have some of the recent development that is going on with industry partners. For example, advanced composite pultrusion development is going on with industry partners Wagners and Allnex. And here again you can see, so like timber poles can be used, and some of them are tested here. And this is about, you can also see in this circular hollow pultruded sections, because of the pull winding technology, you can see that these type of plus and minus 45 or different degrees of angle, while the main angles is at 0 degrees, also fibers are being pulled, but it can be also put into pull winding on cross on the transverse direction. So that has been done, and then we have tested like this circular sections, square cross section, circular sections that has been tested, and bending test, axial test, all of this has been done using the machineries we have got here. So I think I'll go back to this and next one. And while we test, you can see how the failure happens, and then we can see how some of those failures are happening at micro level. So this one, we use the scanning electron microscope technologies to see how the crack is propagating and how the macro level cracks can be starting with the micro level issues. So these are some of the other further testing has been done, and I wanted to just highlight the testing that is going on. And in some cases, like this testing of a circular cross section, where you can have failures at different levels based on the type of loading you will have. And again, one of the important thing is we have various test methods. One of the methods what we have got in our laboratory is digital image correlation technique, where you can use cameras to monitor, and without destroying or putting strain gauges like the sensors. So using the digital image correlation, it is a non-invasive test. You can measure and see how the crack is propagating, and then later you can also do simulations and see how things are going. So we have other fire testing and other matters going on because the temperature impacts of that will be an important factor in using composite material. And then also a different environmental one, either water or moisture with temperature effects are also being studied. So here again, one of our PhD student who just completed his PhD thesis, he has done how to optimize the layup and the geometry. And here again, usually the square cross section has been very popular. Can that be changed in different forms and shapes? So what you can see here is the square cross sections has been changed to a rectangular and more rectangular one. How do we optimize? That has been done initially through numerical studies, and later through various numerical optimization, there's been actual test has been done. So here what you can see here is like the one that is with two or four of the rectangular cross sections, sorry, the square cross sections being connected, that can be done with the one single rectangular sections alternatively. So these are some of the work that is being done. And so if I go back to my presentation in conclusions, what I would like to say here is, so this is again, I think what I wanted to highlight the fact about some of the work what we got the JEC Research Innovation Award. So this is laboratory testing, and this is how at the end, the right bottom, you see the clamp that has been used for external repair of a pipeline. This is a gas pipeline. So that's how some of the R&D work that start with the laboratory work that can result in an actual innovative technology for live pipelines repairs. So we need to understand the challenges. What we have is understanding the material and structural behavior. And as I mentioned earlier, a lot of us have been taught a lot in steel structures, in concrete structures. We are well versed with that. But when it comes to new material, it is not a new material, but similar to timber, the natural material. We have the artificial fiber FRP materials, understand the structural behavior and the material behaviors, and also the failure criteria. Then one of the things every designer will ask is what's the design codes. So nowadays, the American Society of Civil Engineers, they have developed a design standard, so we can use that, and that is being practiced in other places as well. In Europe, they have got Eurocomp design codes, so that can be used for designing FRP structures in actual civil infrastructure. And the other important aspect, for the last 30 years, probably work has been done, and probably 20 years or more, some of the structures are already in place. So we also know the long-term performance. And the important thing, as being in the university, one thing I find is we train our engineers in all of the materials, but not in, it is very few universities train them and educate young engineers in new materials and innovative methods. So that's an important aspect as well. So we have various opportunities with industry partners and also working in research and development. And while we can work on a small scale project or small 1 or 2 testing case studies, but mass scale manufacturing, that's the one that will bring the price down. And we had to target some particular areas. Not everything is competitive. Sometimes steel will, price-wise, steel materials might win or concrete materials might be useful. But FRP materials do win in certain cases, depending on the environmental condition and other aspects, and also the lightweight aspects of that. And in fact, at University of Southern Queensland, at our university, we do train using online education where people can, this online, I'm not talking only in the last 2 years, for the last 15 years, US University of Southern Queensland is well known for its online and external education, and we have been doing online education for the last 20 or more years here. So in conclusion, so composites, I think it's future materials in the civil infrastructure. There are barriers, obviously there are challenges, we can overcome those. And training our engineers is one of the key things. And as engineers, as innovative thinkers, we had to think outside the square. That is an important aspect. And finally, composite is basically bringing different strength and different materials together to work it as a composite. And similarly, we had to have partnership with industry, the government organization, and the universities and research and development places so that we can make it a successful research and development to a commercialization outcome. I think with that, I will conclude my presentation, and of course, my contact details are there, thiru.aravindan@usq.edu.au. Thank you. I'll open for any questions. Thanks.
Thank you very much, Aravindan, for your valuable presentation. It was very nice. So let's wait for the audience to raise up, put the hands and ask some questions. So any doubts, clarifications, all are welcome, please.
Can't unmute. Why is that? I think Mano is trying to, okay, we might have to unmute.
Is it?
Is that Mano is telling he can't unmute? I think people should be able to unmute yourself and ask a question, I think.
Well, Aravindan, while doing that, okay, there is engineer Jagat Upasinghe has put an online message. It was an excellent presentation. Do you have any research or products developed as pontoons and barges?
Okay, that's a interesting question. Like pontoons, not as pontoons, but there has been side barges where for the protection from ships and other places where composites has been used. And we had done a fair bit of testing, and again in the Brisbane River Walk, we had what is known as whalers. That's like a barge, not a barge, but it's a protect.
Sorry, you can't hear. I think. Can you unmute? Please?
Sorry,
Yeah.
I think now can you hear? Okay.
Oh,
I think
good.
in pontoons and barges, there are some places not in Australia. We have done what is known as whalers or on the sides of a river walk that has been done for protecting from ships or other things. But in South Korea, they have used like barges that is protecting the whole pylon system and the bridge pier system. They have used that one and very heavily. So there are areas they have used in some countries, and in Australia they have used to some other port and walkways that has been done, but not as pontoons as such, but it could be done as well. Thanks.
All right, thank you, Aravindan. There's another question from engineer Sandanayaka. He is asking if there is any opportunity to do a joint virtual research project as an undergrad. He must be an undergraduate student, look like. Okay. But I welcome all of you to ask the questions, please. This is one of the training you need to get in. Okay, rather I read up the things, please.
Yeah, I think it is feasible depending on the type of projects and other areas. There are things, particularly if you're doing simulations and others. I mean, a joint collaboration could be done. And I'm aware there are people from other universities have jointly doing research like that. And in some cases, we can also do testing in some other place and test, do the other part here. So those type of things, it comes a lot in having good collaboration, and through your supervisors and academic staff, depending on the university, you can start to talk to suitable people over there where there can be joint collaborations can be done. That is feasible. I think there is
thank you,
Mano is hand this up. Mano,
yeah, Professor Aravindan, thank you very much. It was a very useful presentation. Thanks for it. And just a small question. Now, this fiber composite materials, now we are using in some of the bridges as well. What sort of a limitation it has? That's one question. And the lifespan of these materials, and once, let's say, if it's 50 years, once that lifespan is reached, how do you sort of dispose it? I mean, would that be a problem in the future? Thank you.
Okay, thanks. That's a good and important question. And the lifespan, I think that has been a main question when it comes to civil infrastructure. People have been asking, and we have done accelerated test. And based on that, there is 60 years for rehabilitation or 100 years for some of the new structures has been kind of predicted through accelerated test. But in reality, in the world, there are probably 30 years old structures. All FRP structures are existing in place in Europe, in Australia, and other places. So I think that's where the confidence need to come. And in fact, in Queensland, we have been fortunate with the former director of Queensland Transport and Main Roads. He was one of the pioneers who developed and who took the risk of using that in Queensland Main Roads. So that's an important aspect. I think the other aspect when it comes to what do we do at the end of life, that is a major issue. And there are methods of recycling fibers being used, and that is kind of the current big research is going on recycling materials. and that's an appropriate, there are ways and means, but that is still being studied. But it is important to know about end of life cycle. What do we do, and how do we recycle, or how do we destroy, end of the life cycle? That's an important one. Thanks.
Okay, that's good. One part that the bridges, what sort of limitation?
Okay, limitation wise, I think there are already a lot of councils. Are you based in Australia, I believe?
Yeah, I'm based in South Coast, New South Wales.
Coast, yeah, New South Wales. I think there are with Wagner's, they have used those bridges. Some of them in the form of truss bridges has been used, and full scale, continuous bridges, or span by span type of things has been used. And a lot of the councils have taken they have been quite supportive and taken it. While I think when it comes to like transport and main roads or RMS in New South Wales, I think the main factor is they look at in which bridges we can use this, or which type of roads we will use it. And particularly, I think the secondary roads and regional roads are probably more suitable to trial and get the confidence. I think that's what I would probably say. And other limitations is to be looking at the fire protection, and particularly if there are bushfires and other things, what type of protective coatings and other things need to be done as well, because there are methods of protecting that using appropriate coating technologies. So, and then regular maintenance also need to be done, or inspections. So those are some aspects I would like to highlight. Thanks.
Okay. Thank you.
Hello, Prof. Aravindan. There's another question has come from one of the audience.
Yeah.
What are the latest trends and researches regarding the composites? So I think Prof. Aravindan was saying about the latest research and trends, but if you can just a little bit more elaborate, or
okay, I think when it comes to latest trend and technologies, so FRP rods in concrete had been used a lot in places like Canada, and Australia is also coming on board with that. That is using FRP instead of steel rods. But design standards that is being developed, and new manufacturing technologies being done. So when we talk about FRP in all FRP or full composite material, this is where the trend of technologies of using new manufacturing process to make sure we can develop similar to a steel hollow sections in different shapes and form. So there is developments going on. And in other developments are going on, how do we make use of hybrid fibers, or where you use more than 2 or 3 fibers together, not only glass fibers or combination of glass and carbon, or some other carbon and Kevlar, for example. These type of materials are important. And in fact, I think for the previous question that I remembered the question by Mano, I think one of the limitations, we had to be very careful of what type of resins we are using in our bridge girders. Because if you use epoxy resins, it is quite expensive, but it has much better properties. Polyester resins, I wouldn't recommend in a lot of the heavy civil infrastructure, but in some of the light areas it is feasible. By vinyl ester resins, resin developments and protective system. These are some of the other developments also going on there. So what we had to look at is, while aerospace and automobile industry has developed quite a long way in using composites, FRP in various forms, in very lightweight, very thin materials. But when it comes to civil infrastructure, we are not talking about thin material which will buckle and all that, but we should be able to use that in very effective ways. And some of the new technologies is about, I would call as different modular construction, lightweight construction, even origami type of construction, where you fold the whole thing and then you can develop that one. Those type of things are also coming up. That is important. Those type of developments are going on. I hope that answers. Thanks. And I think someone wanted to share the last slide with my contact details. I think, okay. I think that's believe that's the last slide I need to show here. As I think Jagat asked me to share that one, but I think if you just do a Google search, Thiru Aravindan USQ, you will probably, that will come as the first top in the list there.
Daini has a question.
Yes, go ahead. What's the other question?
Daini, you're on mute.
Hello, Professor Thiru. So this question is actually regarding the railway sleepers. Now, when it comes to railway sleepers, there is like new, like under the proposing limit states, there is a tendency to test the dynamic behavior or the impact performance. So is there any testing that you have done for the testing you have done for this either Wagner's or any other fiber polymer composites under
Yes,
impact testing?
impact or fatigue one? Which one? You're
Not the
talking about
fatigue, not the
impact.
fatigue, the impact. Yeah.
Okay, impact test, some of the things, particularly in the railway ones, what we have done is, one of the main thing when they do, they have the big sledgehammer. That's the one they'll be using in driving some of the things. And the impact kind of test has been done through actual one where you impact it with a big hit with the sledgehammer. Some of them has been dropped from certain heights to see whether there are damages. And there are other specific targeted impact tests could be done as well. So we have done to some level, but I would not have any research as a paper as such, but we had done some impact testing, particularly. I think most of the issues are coming in situ, basically on site. There are issues because the workmen, they will have different things and then something can fall. And in the railway sleepers, yes, they have done certain particular tests to see whether there will be any breakage as such. Thanks.
Thank you very much.
There's another question from Jeremy.
Yes, go ahead, please. Yeah.
Yes, good afternoon,
Yeah.
Could I ask whether the composites are more cost effective than these normal structures, means concrete, other than timber? Yeah, how can you explain that, sir? Cost effectiveness. Yeah.
Cost effectiveness,
Yeah.
my answer is yes and no. Yes and no in a sense. I think one of the important thing is we all look at cost effectiveness of things, but when you talk about a project, it is not the material cost that finally determines the price. It is the cost of how it is manufactured, how it is taken, delivered, and how much site work that goes on, how many days you have to close a road or a railway line. All of that will add to the cost. So on material side, yes, with more and more research and development and manufacturing going, the cost of fibers and resins are coming down. And obviously the timber price is going up because you can't be cutting down timber and because you have to be maintaining the green and the environment. So timber prices are going down and you can't get good hardwood timber. Probably you can't be cutting 100 years old trees now. So timber price is going up. But compared to steel and concrete, yes, as a material itself, in some cases, the cost of steel or concrete or prestressed concrete might be cheaper, but the prices is also coming down in composite materials. But the other one is the delivery and installation. If you wanted to do a concrete bridge rehabilitation, you will be closing that road or have one side closed and the other lane open for a couple of weeks or more before you do that. Whereas in a composite one, you can take, install everything, and within a couple of days or 2 to 3 days, the bridge can be reopened. So that is one of the aspects of how we consider the cost aspects. And some others, that's where I say we don't target everything in anything, but there are areas, particularly where steel will start to corrode in a corrosive environment. In that case, in a salt closer to the seashore and other places closer to the sea. In that case, can we use composites? In that case, yes, it is much more sustainable, longer lifetime compared to steel structures. So those type of things are something to be looked at. And in fact, I can say Wagner's, they are exporting some of these girders, as well as they have used that in electric light post as cross arms, the cross girder that comes into connecting all the lines. They have exported to Malaysia and various other places, including South America, where they find it is cost effectiveness, and that has been beating the price in some areas there. Thank you.
Yes, sir. Thank you.
Any other questions?
Yes, Prof. Aravindan. Yeah. Okay. You touched about the timber. That's a very good point. So in Australia, a lot of construction, the major construction material used is timber. In if you look at everything totally put in. So have you or can you any applications for the FRP, fiber reinforced polymers, to strengthen the timber timber properties, especially in getting the laminated timber veneers, lumber timber beams kind of thing? And also, is there any applications developed on the residential flooring materials? We had been using only the very conventional ones. So they are like quite similar to the plywood, but they are a little bit advanced. They are called the gelotang floors. It's a resin mixed fiber particles. So is there any other applications to improve the strength and make it cheaper? The timber has gone up like 4-folds now.
Yeah, I think that's there are, hybrid timber, or where, resins and other areas, other things are mixed together and put as a panel type of one that is being currently developed. And what I think one of the biggest challenge in bringing some of the sandwich panel technology and others, it's the cost and the demand for manufacturers or to develop full-scale manufacturing technologies. So I think that has been the challenges there. But currently, I think there are still work is being done on that, particularly on timber floors or alternative timber floors type of one. Composite panels are suitable, but I think there is still certain work is going on there. So that's why I think the pultruded technology has been well developed, and that is making way into commercialization and all that. But the sandwich panels or suitable panels is still in the process of R&D to just a few case studies. So I think, but over time, that is likely to come up more.
All right.
But the other aspect on I wanted to highlight is the advantage, some of the girders what we used in timber girders replacement. Why we had to go with the composite one is when 5 of the girders in a 10 meter, those days it is 30-foot bridge. If you want to replace one of the logs there, you cannot replace that with concrete or steel, because the concrete and steel EI value is much higher. So we engineer the EI value to the same as the log of the timber girder. So that has been the advantage, where you can engineer the EI value, and particularly at serviceability state level, EI value becomes the main factor when you're talking about a grillage analysis and systems. So that's the way that has been engineered to make sure it is meeting the existing timber girders stiffness value. and that way it can work uniformly, complementing each other. Whereas if you are replacing a whole new bridge, that's a different story. Then the price competitiveness will come with different materials. Yeah, thanks.
All right, thank you, Aravindan. Any other questions from the floor, please? Please feel free to put up your hands.
I know we have got Vidushan there. You have a materials engineer. Do you have any question from your perspective? Yes, Vidushan is putting his hand up.
What are the future developments in the material aspect to develop the infrastructure usage, especially for civil infrastructure?
I think on the material side, it will be mainly the materials development. What kind of glass fibers? Because we have got different e-glass and other material, and the durability of the glass fibers will be quite important. Because glass fibers is the most heavily used in civil infrastructure compared to carbon fibers or aramid fibers. Aramid fibers and carbon fibers are used for very specific aerospace or automobile type of ones. And the other one is the resin, and it's, I would say, particularly on the glass transition temperature and improvements in its properties, because as you probably know, the polyester resins have got very low TGA values. It will start to melt around 60 degrees, 65 degrees, whereas vinyl ester is a bit more. It can go up to 80 plus, and epoxy is 120 plus. So these are some of the things. The improvement on the temperature is important for us as well. Thanks.
Thank you so much.
Yeah, I think one of the important thing what I learned after coming to composites, while I started back in Sri Lanka more on concrete designs, then went to Japan and did pre-stress concrete, post-tensioning, external post-tensioning, all of that. When I came to Australia, then I was using the external post-tensioning, then FRP material as FRP materials to be used in concrete structures, rehabilitation, and all FRP. I think when it came to these type of things, what I learned was sometimes we had to go and work with complementary people outside our engineers, like polymer chemists, chemistry people who develop things, and materials engineers who develop those new materials and bring the chemistry, analytical chemistry, understanding how do we test. All of that was quite important. So we had to work in a multidisciplinary team to make this a reality. I think that's an important aspect. I think everyone, we should understand when you are, whether you are a civil or electrical or mechanical engineer, you still have to work when it comes to other aspects and new work to be done. We'll have to work with different people and outside our team as well, outside our area of discipline. Thank you.
All right, thank you, Aravindan. So with this one, we want to invite our Vice Chair, Engineer Rasika, to give the vote of thanks. And I also will suggest whoever want to continue with Prof. Aravindan and have discussion, the link will continue. So you can have a chat after the formal presentation is over. We all are welcome to do so. He is a education counselor too, so you could ask a lot of questions about career counseling too. Now let us welcome our engineer Rasika Gunavatana to give a vote of thanks for our Professor Aravindan, please.
Thank you, Saudi. Can you hear me?
Yes, of course.
Yeah. Good evening to Professor Aravindan and IAS New South Wales Chapter Chair Saudi, my fellow committee members, and ladies and gentlemen. It is a great pleasure to propose the vote of thanks on this occasion on behalf of IAS New South Wales Chapter. Let me first and foremost thank our distinguished presenter, Professor Thiru Aravindan, for delivering this informative and interesting presentation. We could see that many questions came, which indicates that it's a very interesting one. We are grateful for the time and effort Professor Thiru Aravindan took to share your thoughts and experiences with us. Secondly, I take this opportunity to thank our chair, Engineer Soti, who took initiative to coordinate with our distinguished presenter to make this event happen. I also express our sincere thanks to Dr. Manasi, our IESL New South Wales chapter secretary, and Mr. Chamila from IESL headquarters in Colombo for the communication work and support extended in setting up this Zoom event. Next, I would like to thank our wonderful audience for your interest in the presentation as well as the valuable questions. Last but not the least, I thank our committee members of the IESL New South Wales chapter who work behind the scene and for your cooperation in making this presentation a resounding success. One more thing before we wrap up, if any engineers residing in Sydney or Canberra or even in Sri Lanka who are not with IESL New South Wales chapter, I would like to invite them to subscribe our mailing list so you will receive all the communications regarding the events and lectures. I will just briefly share my screen to show how you can just go to that website. Give me 1 minute. So hope you can see. If you go to ieslnsw.org, can you see my screen?
Yes, I am able to see here.
Yeah, so just go to ieslnsw.org and here you have subscribe button and just click subscribe to our mailing list. So you will get this kind of a small form to fill. So you can just click subscribe and you will get all the information. And sorry. So we have this exciting list in future, list of presentations planned. So I hope everyone will join the next presentation from Australia or Sri Lanka or wherever. Thank you so much. Good night, everyone.
Thank you, Rasika. Okay. So whoever want to have a chat with Aravind, then we can continue to have some more time with us, please. I think Geetani is here. Manasi?
Yeah, I'm here.
Yeah, Geetani, I
Okay.
saw Geetani.
You should have greeted
Hi, Arvindan. How are you?
Good. How are you? Nice
I'm
to see
good.
you. Yeah.
Nice to see you.
You're probably
Yeah,
from Canberra.
Yeah, I'm from Canberra.
Canberra, yeah. Okay, good to see you. Yeah, Vasanta is fine. She has gone home. I'm still presenting from office.
Okay.
Others, anyone who wanted to ask any questions, feel free to ask things. Anyone who want to clarify.
Yeah, there were some people interested really about their career and doing some research. So whoever, please come and ask those questions. Well, they all
Dilipa
are.
is there. Who is that Dilipa? Is that our batch Dilipa or someone else?
Looks like our Dilipa.
That's so.
Hello, Dilipa.
Not sure, but maybe
Okay.
I'm not sure.
Rohita was here too, your friend.
Who?
Rohita was here too.
Rohita. Yeah.
I think he left. Looks like he left. Yeah.
Excuse me, Professor Aravindan.
Yeah.
Hello, sir. I'm Supun Sandanayake from Sri Lanka, studying
Yes.
material science and engineering at the University of Moratuwa.
Yeah.
Sir, I'd like to know what are the initial steps do we have to take after our graduation for higher studies?
Okay. Are you same batch as Vidushan or someone
Yeah,
else?
yeah. Yes,
Okay.
sir, we do. Yeah,
Okay.
Yes, same.
Okay, same batch. Okay, Vidushan can give some advice as well. He has been asking me on a few things, but I think what is important if you are thinking of a postgraduate studies, whether in Australia or overseas, some other places like Canada or US or UK or Europe, I think what will be important is to get a good undergraduate, do a good project, and also get some good results. Minimum will be a second-class upper if you wanted to go for a direct PhD, but if you were thinking of a scholarship, probably first class would be quite important. But not only first class, but your English language skills and IELTS or similar like the TOEFL and others will be also important because they look at English communication and English test is one of the requirements now. And while you are doing your undergraduate projects, it's also important to have a good network. You talk with your professors, your supervisors, and see who else are working in that. So that's where your LinkedIn profile and networking will be quite important. And then you can also start to write in a conference, start with a small presentation, either in a local conference. ISL, I'm sure they have conferences regular basis for students and alumni, because that's another aspect you have to look at as well. And that way you can start to have additional things added in addition to your qualification from a university degree, but you will also have other special things added to that. And leadership in many, good teamwork skills, those type of skill, networking will be important. I hope that gives a bit of an idea.
Yes, sir, of course. Thank you very much, sir.
Because I can remember I did my project back, I think so, I think we finished in our 1991.
Yeah,
my undergraduate project, I presented at the Institution of Engineers annual forum. They had the annual conference in where that place, Vijayarama of that one. The number seven Vijayarama or something. That's what I remember. The address of engineers of Institution of Engineers Sri Lanka. So in 91 October, I presented that in the annual conference, and it was published in the proceedings. That was my undergraduate project. It was a joint project, myself, Vasanta, and Saraswati, three of us. We presented about spreadsheets, Excel those days, or not even Excel. It is Lotus 123, using spreadsheet for designing to BS 8110. That was our spreadsheet that we developed, and I presented about it. So that's kind of the thinking. It doesn't matter what you are using, but you are using some projects, communicate it and present it. That way you can start developing skills of writing papers and starting with conference and some other, and also presentation and good writing skills. Thank you. Any other questions anyone wanted to ask?
Any other students from Sri Lanka? Please welcome to talk.
There is nothing as a dumb question. Not asking the question is the dumb thing. So if you have anything to clarify, yeah.
It is a good platform for us, for you all to get practice talking with the people, All right. Okay. So
Yeah, I think I would like to thank the opportunity for Nyanasodi and also Rasika for organizing this, and it also gives an opportunity with the current days technology. We can have participants coming from Sri Lanka, in Australia, from different parts, and you can either listen from your home, or you can present it from your home, or you can, while driving in the car also, you can still listen to this. So there is some of the aspects of the technology, but make use of that to the best for your career and your, whether you are an undergraduate or postgraduate or working. There are things that goes on, so that's a good opportunity. Thank you very much. Thanks everyone.
All right, thank you. Thanks, Aravindan. Thanks,
Thank you.
you.
We'll
everyone.
catch up,
Our
yeah.
Thank you
committee.
very much.
Thank you, Geeta.
Okay,
Thanks
we
for
will
this.
close up the meeting. Yeah.
Yeah.
Okay, thank you.